Hi everybody, here we are, Chapter 8. This is a bit of a long one, but an important one. So let's get to it. So hopefully you've read the chapter, you feel ready to go. We're going to be learning about confidence intervals and interval estimation, and we're going to do basically four things. We're going to do an interval estimation where we know the standard deviation of the population. We're going to do one where we don't know the standard deviation of the population. I'm going to show you how to calculate sample size for a given margin of error, and then we'll do an interval estimation for a proportion. Okay, so what are we trying to do? We're trying to say something about the underlying population data by creating an interval, a range within which we think that population parameter is going to fall. And so the first thing that we're going to do is try to create this bound, this confidence interval that it falls within. So the general form is we're going to look at this x bar, the sample mean, and add to it and subtract from it a margin of error. And we usually use 90%, 95%, or 99% as our confidence intervals to create how big of an interval that we think the population parameter will fall within at those different confidence levels. So what's the formula for the margin of error? We look at our x bar and we add or subtract to it a z-score. You guys know what those are from our Chapter 6 work. In this case, we divide it by, we take the alpha divided by 2 to come up with the z-score. What is alpha? It is what is 1 minus our confidence interval. So if we're doing a 90% confidence interval, 1 minus 90% would be an alpha of 10%. We would divide that by 2, 5%, and we would look for a z-score with 5%. I will show you the z-scores. You don't need to calculate that. And then we multiply that z-score by the standard error that we learned that in Chapter 7, standard deviation because we know it from the population divided by the square root of n. Okay, so let's go ahead and here's the z-scores. You've got a 90% z-score that corresponds to, a 90% confidence interval corresponding to a z-score of 1.645, 95%, 1.96, etc. So let's do this. What does it mean and how do we do it? Let's say we want a 90% confidence interval. What do we construct? We do x bar plus or minus the z-score that corresponds to that. We just saw that on the previous slide, 1.645, and this refers to the standard error. So that's standard deviation of the population divided by the square root of n. What we do is we use this formula for the interval estimate, and what that tells us is we're 90% confident that the population mean will fall within that range. So we could say that this interval has been established at the 90% confidence level, sometimes that's what people say, and that 0.9 is the confidence coefficient. All right, let's do an example. Let's say there's Discount Sounds. It has 260 retail outlets. It wants to locate a new outlet, and something that it needs in order to be successful is to know what the mean annual income is of individuals in that area around that new store or that new location. So they take a sample is 36, and they find that the mean income from that sample is 41,100, and the standard deviation is believed to be 4,500. They want to get a confidence interval and know within 95% that the population mean annual income will fall within this range, and that will help them budget. So we go ahead and we use our formula, z-score, alpha divided by 2. We know that's a 1.96 confidence level z-score. Multiply it by 4,500. That's the population standard deviation divided by the square root of n, our standard error. And that is our margin of error, $1,470. So to 95% confidence, I forgot level, the margin of error is 1470. We just go ahead and add that or subtract that from our x bar. So 41,100 plus or minus 1470. Here is our confidence interval at 95%, our interval estimate. We can say we are 95% confident that the interval contains the population mean. So 39,630 to 42,570. Okay, so that's the technical way of doing this. Something interesting to note is that as you want to get more and more confident that your interval estimate will contain the population mean, or mu I should say, so as you're going up in confidence level, notice if we were to have done that formula, and you can try it on your own if you'd like, the margin of error will increase, which will widen your interval estimate. And that will always be the case, partly because the z-score is getting higher. But really, conceptually why is because to have a higher degree of confidence, you need to have a broader interval estimate that will have that population mean fall within it. Okay, don't fret because we can do all this on our calculator. So let's just say we want to do a 90% confidence interval. What we would do if our standard deviation is 3 and our x bar is 68 and our n is 36 is we would arrow down to z interval. When we go to our calculator, stats, enter, and you go down and you do, this is in the tests, so you do z interval test, and then your standard deviation is 3, your x bar is 68, your n is 36. You plug in a confidence interval, make sure you do it in decimal form, calculate, and boom, you get, there is your interval estimate. So that is at a 90% confidence level. All right, couple other things. We need to know how to do a confidence interval when it is not a normally distributed, when we don't know our population standard deviation. So prior we did, and we could use z-scores. If we don't know what the population standard deviation is, we can use the sample standard deviation to approximate it, but we're going to use a new distribution, a t-distribution. It's sometimes called the student t. And that'll just give us a t-score rather than a z-score in our formula. We also need to know something called the degrees of freedom. So let me show you this. This is what the student t-distribution looks like. It's got a symmetrical shape around the mean. It's a continuous probability distribution, like a normal distribution. The larger the sample size, the more it starts to approximate what is our standard normal. Okay? Degrees of freedom, here you see for 20, that's always n minus 1. So the bigger the sample size, the more it's approximating the standard normal. For a lower sample size, here this would be n minus 1, it must have been a sample size of 11. The degrees of freedom being 10, it's flatter. Okay, I'm going to show you how to come up with the t-score. The formula is the same. We take our x bar plus or minus a t-score now though, and instead of using our standard deviation, we use s, so it's similar, divided by the square root of n. Remember, this is our standard error. How do we get this t-score? Okay, we need to use something called inverse t, which is very similar to inverse norm. Let's set up a problem and then we'll do it. So here's a problem where we don't know the standard deviation of the population. We're saying that there's a reporter for a student newspaper writing an article about off-campus housing costs. They take a sample of 16 one-bedroom apartments within half a mile of campus. They get a sample mean of $750 per month of rent and a sample standard deviation of $55. Now let's say we want to do a 95% confidence interval for this to figure out what the true population mu, what it will fall within. We need to do our t-score calculation. So the formula is similar, right, for the confidence interval, x bar plus or minus t. We do alpha divided by 2 still. Where do we get the t-score? I don't have a chart to tell you because we need the degrees of freedom. There's going to be variation in our t-scores, unlike with the z-scores. So we go and we use our inverse t. Remember how we used to go to inverse norm? So go second function stats, vars, go down to 4. That's what it is on my calculator. And do inverse t rather than inverse norm. You're going to put in the area that's going to correspond to the confidence level that we're looking for, and then you need to put in the degrees of freedom. So remember, the area is based on the probability under the curve, and if we're doing it in 95% confidence interval, that means that we have 95% of the data that we want to fall around the mean. So there's 5% left over in the two tails. So we have to divide those two tails by 2, and that's where we get this 0.025 in a tail and 0.025 in the other tail. So what comes out of our calculator is left to right, so we add that, oops, sorry about that guys, we add 0.025 to our 95%, and we want to find a t-score that corresponds to 0.975. Okay, let that sink in for a little bit. Then you put in the degrees of freedom, n minus 1, 16 minus 1, that's 15, and we get a t-score of 2.131. Now it's easier. We go ahead and we plug in x bar, right? That was our 750 sample rent, plus or minus the t-score we calculated, 2.131, times the standard error using sample standard deviation, 55 over the square root of n, and we get 750 plus or minus 29.3, and that gives us a confidence interval of 720.70 to 779.30. By the way, you can use your calculator for this. Okay, I highly recommend doing it. Same process that we used before, just make sure you do it as a interval test. Okay, sample size for interval estimate. Here's another thing that we can do. Rather than sometimes calculate the interval estimate, maybe we know what we want the interval estimate to be, and then we want to say what sample size do we need to get that. What does that mean? It's like it's expensive to go out there and survey. It's expensive to have a big sample size. So maybe you want to know what's the lowest sample size that you need in order to get a certain margin of error. So what we do is we just take the margin of error calculation and we let E be the desired margin of error. Maybe, and then what we do is we rearrange and we solve for N. And that tells us the sample size we need for a given margin of error. All we did is take this formula, rearrange it like this. So let's try this. So let's say we've got discount sounds again. And we've gone through the whole thing, their mean annual income, etc. But now we know at this 95% confidence level that they want to know within plus or minus $500 what sample size they need to say for that precision. So we are going to plug in, that's our desired margin of error, is $500. We rearrange everything at a 95% confidence level, use the z-score that corresponds to that 1.96, and we just are solving for N. So z-score squared, this is rearranging this formula here, times the standard deviation squared divided by our desired margin of error squared, and we get that our desired sample size of 312 is what's needed to reach a desired precision of plus or minus 500 at a 95% confidence level. Okay, couple more things. We have a population proportion formula. So if it's not an actual number, if it's a percentage, if it's a proportion, if it's p bar, look, the formula is similar, z alpha divided by 2, z-score alpha, but this is our standard error of the proportion. Learned that in a prior chapter, p times 1 minus p over n, the whole thing square root. Let's do an example. Let's say that there's an election campaign and PSI Inc. has conducted random phone surveys and found that 220 registered voters out of 500 contacted favor a candidate. So we could set up a p-bar proportion, 220 over 550, and we'd want to develop it at the 95% confidence level. So what do? We go ahead and we do p-bar plus or minus our z-score. If it's 95%, we still use the 1.96, right? What's our p-bar? It's going to be 220 divided by 500. That was from our problem. So 0.44 plus or minus 1.96. Plug in p times 1 minus p over n, the whole thing square root. Boom! We have our confidence interval, 0.3965 and 0.4835. Our calculator can do this as well. So you would go to the calculator, you do the interval test for proportion. I can work through that with you. If you need to email me about that, please do. We could also rearrange this for sample size. We can have a desired margin of error as well, and then we solve for our sample size. We just rearrange that formula. This can go on your formula sheet. I need to tell you one little caveat about that, and that is sometimes we don't know what the population proportion is. So what we do is we use this, 0.5, if we don't know. So that's what we would plug in for those sample size determinant ones if we have a desired margin of error for a proportion. If you don't know what the proportion is, you just plug in 0.5. So let's do an example since I have some time. Here's an example. Suppose that PSI, oops, so sorry about that. Suppose that PSI, let me get back here, would like to have a 99% probability that they're within plus or minus 3%. How large of a sample size is needed for that? Here's our formula. That was from the prior slide. What are we plugging in here? In this case, we actually have all the data we need. We know what the z-score is for 99% confidence. We know what the p and the 1 minus p is that was given in the problem. And we know what our desired margin of error is, 0.03%. So we solve and we figure out that 1,817 would be needed to reach a desired precision level of the 0.03% at the 99% confidence interval. Okay, I know this is a lot to take in and it's a long video, and just know that there's going to be practice in lyrics and in your assignment, that's your chapter 8 handout problems, and I'm always here. So email me, please. I want to be of help, and I wish you all luck and stay in touch, and that's all for now. Bye.